this is the model that we want to use for adaptive system identification. We're going to use adaptive filter, LMS, for this. These are measurement data. And y of I is also measurement data. And unlike these values, the values with this hat sign are estimated or computed values. I want to represent this equation compactly using vectors. In case we define our perimeter vector wi like this, a sub 1 of I hat and b sub 1 of I hat transpose. This is our w vector or perimeter vector. And we can also define our data vector t of I, which is this one here and this one. So it will be x of I minus 1 and y of I minus 1 transpose. Y of I hat is data vector t, and this is data vector. Data vector t of I transpose. This data vector is a column vector, x I minus 1, y I minus 1. So t of I transpose, you're basically converting this into a row. It will be like this without this transpose sign. So we have a row vector here, and you multiply that by column vector, which is w of I. And again, this is a column vector. And since our goal is to find optimal perimeter values, we want to find optimal w of I vector, w opt of I vector. The basic idea of LMS filter is to find W opt of I iteratively such that expected value of error squared is minimized. And what is this error? If you recall, this error is the difference between real Y and estimated or predicted Y. We provide this error to adaptive filter, and what LMS does is it squares the error and it tries to find out these perimeter values that minimize this squared error. And that is why this LMS has this name, least mean squares. Least squares comes from this error squares, and mean comes from this expectation. And this becomes convex optimization problem because this function is convex function, something squared.